Pre-AP, pre-calculus. This is notes 10.5, solving trig functions. Trig equations, I should say. So let's take a look at something that we've done in the past and try to bridge the gap between what we've learned previously and what we're trying to accomplish in this lesson. Solve the equation, finding two values of theta such that theta is between 0 and 2 pi, including 2 pi, not including 0. Round your answer to the nearest thousandth of a radian if needed, but we're probably not going to need to do that. We know that if we want to get theta by itself in the equation, sine of theta is 1/2, but we are going to apply sine inverse to both sides of the equation. That is the inverse of sine, that's why it's called sine inverse. It gives us theta by itself on the left, and on the right, we have sine inverse of 1/2. Now, from your knowledge of the unit circle, you probably know right away what this answer is. Let me just refresh your memory. First of all, if sine of theta is positive 1/2, that means that y is positive. So we're in quadrant 1 or quadrant 2. Let's assume that we're in quadrant 1. So you can look at this as being the y value is 1/2, or you can think of it as the y value is 1 and the radius is 2. I'll just do 1/2 because it's what we're used to. What would that make the reference angle for this? That's going to make the reference angle 30 degrees, which in radians is pi over 6. Now the same triangle can be made in quadrant 2, because that y value is also positive. It's also positive in quadrant 2. That makes this angle here 6 pi over 6 minus pi over 6, which is 5 pi over 6. So I am suggesting that the answers to this problem, there are two of them, is going to be pi over 6 in quadrant 1 and 5 pi over 6, the terminal side, terminates in quadrant 2. Let's take a bigger look at this graphically. If we were to graph the equation y equals sine of theta, that would look like this. I've taken the liberty of also graphing the line y equals 1/2, which represents this. And then this red curve represents y equals sine of theta, which represents the left side of this original equation. Where do they intersect? Well, they're intersecting here at pi over 6 and intersecting again at 5 pi over 6, which is the answers that we got from using the unit circle. So that's why there are two answers, because as we see, the curve comes up and hits 1/2 and then comes back down and hits 1/2 again. And it won't hit it again until it gets to the next period. Since we're supposed to find theta between 0 and 2 pi, that only happens twice in this period. Could happen as few times as once, could happen as many times as 2 times between 0 and 2 pi. What would happen? So that concludes this problem. This is the answer. I'm just trying to give a little explanation of what's going to happen next. What would happen if we had sine of 2 theta is 1/2 instead of just sine of theta? How is it going to affect our answers? Well, I hope that you remember that if we're multiplying the inside of the function by 2, it shrinks the graph horizontally by 1/2. That means, this is just a rough sketch, that this graph is going to make a complete period, that was a little off, between 0 and pi, and then it's going to make another period between 0 and 2 pi. So if that happens, you see that we're going to have 1, 2, 3, 4 answers. The number of answers just doubled. This 2, once again, we're going to do an actual problem of that. I'm just trying to give you a snapshot of what's going to happen. This 2 here tells you that your number of answers are going to double between 0 and 2 pi, because you can fit 2 full periods between 0 and 2 pi, where you could normally fit 1. Let's do an actual example like this, and hopefully this is going to make some sense. Solve the equations below, find exact solutions when possible. The interval from theta is between 0 and 2 pi inclusive. Round your answers in your thousandths of radian if necessary. Same directions that were up above. So our work for this starts out to be the same. If we apply sine inverse to both sides, we're going to get 2 theta is sine inverse of a half. Now at this point, do not get theta by itself. Just get the angle by itself, which it currently is 2 theta. And let's answer this question. What is that going to make theta? Well, what's that going to make 2 theta? We know from our work above, 2 theta is going to be pi over 6 and 5 pi over 6. How do we know that once again? Just a quick review. If sine of 2 theta is 1/2, that means y has to be positive. That's in quadrants 1 and 2. And that we know this reference angle is pi over 6. So one of the angles is pi over 6. The other angle is going to be 5 pi over 6. That's how we get those 2 answers. Once you've found those 2 answers from the unit circle or from drawing the 1/2 in the coordinate plane, and that can be done with a unit circle or of a different radius, only then do you get theta by itself. If we get theta by itself, we're going to be dividing each of these fractions by 2, same as multiplying by a half. We're going to get pi over 12 and 5 pi over 12. Now these are not the only 2 answers. There has to be 2 more answers. And the reason, once again, as was pointed out up here, this represents y equals sine of theta. If it's 2 times sine of theta, that means this whole graph here gets, I can't do this with the iPad apparently, the whole thing gets shrunk horizontally by a half, which means the number of answers are going to double because I'm going to have 2 of these periods in the same length that it would be for a normal period. Let me show you what that looks like graphically, and then we'll try to come to a conclusion of how we're going to find the answer. This green curve represents y equals sine of 2 theta. Notice that there is a complete period from 0 to pi, and there is another complete period from pi to 2 pi. So the question is, how many solutions are we going to have to this? We've already concluded there's going to be 4. We got this one right here, which is pi over 12.5, which is this answer. We have 5 pi over 12, which is this answer right here, which represents this answer. So then the question is, how do we get these other 2 answers logically? Well, this point here and its corresponding point here are going to be pi units away. Normally they're 2 pi units away. Since our period got cut in half, they're going to be pi units away. So if I take pi over 12 and I add to it 1 pi, which is 12 pi over 12, that's going to give me 13 pi over 12. That's my third answer. Similarly, this dot here is 1 period away from this dot, pi units. So 5 pi over 12 plus 12 pi over 12, well, that's going to give me 17 pi over 12. And that gives me all 4 answers. This graph that you see down here, you don't need to draw this graph to do these problems. I'm just trying to give you a visual representation of why there are 4 answers. We can see that this purple line, once again, represents y equals a half, and it's intersecting the green curve 4 times. 1, 2, 3, 4. We got answers 1 and 2 from the unit circle. We got answers 3 and 4 from adding pi to the answers we got from the unit circle. Let's check out another one, see if we're getting this. Number 2, tangent of 2 theta is negative 1/2. Well, first of all, when is tangent negative? Tell you what, let's go back to number 1 real quick. When you first start these problems out, I think that you would want to jot down which quadrants you know the terminal side is going to fall into. So that's 1 and 2 because sine is positive in 1 and 2. When is tangent negative? That's when x and y have different signs. So that's going to happen in quadrants 2 and 4. Quadrant 2, x is negative, y is positive. In quadrant 4, x is positive and y is negative. So we know that's going to happen in those quadrants. So step 1, figure out what quadrants they're going to fall into. Step 2, get 2 theta by itself. So 2 theta is going to be tangent inverse of negative 1. Well, when is tangent of an angle equivalent to negative 1? If it's in quadrant 2, that makes this angle pi over 4. That's a 45 degree, 45, 45, 90. This is 1 and this is negative 1. Or you can think of them as negative square root of 2 over 2 and positive square root of 2 over 2. That's going to make this angle 3 pi over 4. This is also happening once again in quadrant 4. Makes the reference angle pi over 4. But the angle that we're looking for is the angle in standard position, which is 1 pi over 4 short of being 2 pi, which is 7 pi over 4. So that means that 2 theta, not theta, but 2 theta is 3 pi over 4 and 7 pi over 4. Once you know those, then get theta by itself. So step 1, figure out what quadrants you're in. Step 2, get 2 theta by itself. Step 3, figure out what 2 theta is equal to. And then step 4, figure out what theta is equal to. So we're going to multiply both sides by 1/2. It's going to give us 3 pi over 8 and 7 pi over 8. Now how do we find our other two answers? Well, we take what we're given and we take what we found out and we add pi to each of those. Pi as a denominator of 8 is 8 pi over 8. So we're adding this. 3 pi over 8 plus 8 pi over 8 is 11 pi over 8. And 7 pi over 8 plus 8 pi over 8, that is 15 pi over 8. And I said 8, here I wrote a 4. My apologies. Make sure that your answers all fall between 0 and 2 pi, and each of these do. So those are our answers for that. Let me show you what this looks like graphically once again. This is not required to do these problems, but I'm just trying to make sure that you understand what's the haps. So initially, this was equal to negative 1/2. So this red line that you see here is y equals negative 1, not 1/2, negative 1. And the black curve represents y equals tangent of 2 theta. So we found from our work, let me highlight some of this, pickles worth. All right, so we got this answer is represented right here, and this answer is represented right here. These other two answers, which I'll highlight as purple and green, the distance from here to here is exactly 1 pi. The distance from here to here is also 1 pi. Just showing you how that shakes out looking at the graph. And let's continue and check out some more examples. Directions and some little over-explaining here, some mansplaining, if you will. Up until now, we have only solved equations that contain a single trig ratio. Often, however, we encounter equations that contain more than one. For example, the equation has both sine and cosine in it. When we encounter this, our goal is to see if we can rewrite the equation in terms of only one trig ratio. So let's see if we can do that. So our goal here, so the directions of this might be, see if you can rewrite this equation in terms of only one trig ratio. That means that this answer that we're going to get is only one of 6 potential answers. There's 6 different answers for this that are correct because there are 6 trig ratios. So if I want to get a single trig ratio, That means I want the other side of the equation to be a number. Just like for the previous problems, we had trig ratio equal to a number. Trig ratio equal to a number. This already has a number. So I'm going to get that number by itself. I'm going to divide both sides by cosine of theta. It's going to give me sine of theta over cosine of theta equals square root of 3. Are we finished? No. There are two goals here. We want one trig ratio. We want it equal to a number. We got the right side part. We got the right part correct. It's equal to a number. The left side is not one trig ratio. But I hope that you remember that sine over cosine is tangent. So tangent of theta is the square root of 3. Now, I believe we're supposed to actually solve this. So what would theta be? Well, when is tangent positive? Tangent is positive when x and y are the same sign. It happens in quadrant 1, and that happens in quadrant 3. I'm going to go non-unit circle on this because that's easier for my brain. You can go unit circle if you want. If I'm going non-unit circle, I'm saying the square root of 3 is the same as square root of 3 over 1, which makes y the square root of 3 and x 1. In quadrant 3, that makes y negative square root of 3 and x negative 1. What does that make my reference angle? Well, that's going to make this pi over 3. That makes this pi over 3. So my answer, well, I should solve the equation for theta. Theta is going to equal tangent inverse of square root of 3, which is going to make theta pi over 3. And then here, that's going to be 4 pi over 3. Don't need to add any more angles to this because let's just assume that we're supposed to do one from 0 to 2 pi. The directions don't tell us. Hopefully they will when we're doing real problems here in the homework. All right, let's check out number 4. I'm going to choose to get cosecant of theta on the left. To do that, I'm going to multiply both sides of the equation by sine of theta. On the left, that gives me 4 sine squared of theta. On the right, these are reciprocals, so we get 1. If we then divide both sides by 4, we get sine squared of theta is a fourth. Then if we were to square root both sides, we would get sine of theta is plus or minus 1/2. And I actually think the directions for this, well, there aren't any directions. If the directions were just to write it as one trig ratio, then we're finished. If the directions were also find theta, well, then we're not finished. So we'll just stop here for this problem, and then whatever the homework tells you to do for that, that's what we would do. Here is some really important things. I'm really excited about doing this finally in this chapter. What we've done for the most part is when we're trying to solve, not solve, but trying to verify that something was an identity, we'd make the left and right sides equal. A lot of times we would just change everything in terms of sine and cosine, and that would work out great. Or there are some problems that doesn't work out well for. For some problems, factoring is the best, easiest, quickest, fastest way to do the problems. And I'm excited about this because we haven't done a lot of factoring this year, and I would like to get better at factoring. So what are some different factoring rules? Well, if it's a binomial, like this one is, there's 2 terms, could be one of 3 things. Now, first of all, always factor out the greatest common factor. This one, the greatest common factor is 1, so we don't have to do it. Then, if it's a binomial, it could be the difference of 2 squares, the difference of 2 cubes, or the sum of 2 cubes. This problem is the difference of 2 squares. How do I know? This is a perfect square. It's a square that's 2 sine of theta by 2 sine of theta. This is a perfect square. It's a square that's 1 by 1. So that makes this factor into a 2 sine of theta minus 1 and a 2 sine of theta plus 1. All I'm doing right now is just showing you how these things can factor. That's all I'm doing. These aren't real problems. These are going to be parts of future problems. Difference of two squares. This next one, GCF. What's the greatest common factor? Well, this has a cosine, this has a cosine. So we can factor that out to the front and get cosine of theta. What are we left with? Sine squared of theta minus 4 cosine squared of theta. This is a difference of two squares again. It's going to factor into sine of theta minus 2 cosine of theta times sine of theta plus 2 cosine of theta. Number 7, difference of two squares again. This is sine of theta minus cosine of theta and sine of theta plus cosine of theta. So if you're thinking at this point, well, you've mentioned difference of two squares several times. What, pray tell, are you talking about? Let me remind you with something more conventional. X squared minus 9, I think we all know, factors into an x minus 3 times an x plus 3. Perfect square, perfect square. Square root of the first term, square root of the second term, you make 1 plus and you make 1 minus. You've been doing that for quite some time, but not with trig functions. Number 8. This is a trinomial, 3 terms. Now, if you're lucky, the leading coefficient here is a 1, which it is. If the leading coefficient is 1, that's the easiest type to factor. What we need is, we need two things that multiply to get negative 15, two things that add to get negative 2. Those numbers that work out for that is a negative 5 and a positive 3. Now, this only works, what I just said, if this leading coefficient is 1. We'll see in the next problem what to do. It's a more universal approach when it doesn't have to be 1, but still works when it is 1. This is going to break down to two binomials. If the leading coefficient was 1, this is called a monomic trinomial. We just square root this and break it apart evenly. Sine of theta, sine of theta. These two numbers, the numbers we found, ends up making this magic work, so we get this right here. Just to confirm that this works, sine times sine, sine squared. Negative 5 times positive 3, negative 15. If I multiply sine times 3, we get 3 of those, and the negative 5 times sine is negative 5 of those. Negative 5 and 3 is negative 2, which makes the middle term. All right, number 9. You could still use the Australian method, but I'm probably not going to ever mention that again in the future. I'm just going to show you how to factor this stuff correctly using splitting the middle term. So here's a trinomial, and the leading coefficient is not 1. So here's how this works. It's very similar to how we did the last one, but it's a little more technical. We need two things that multiply to get the first term times the last term, which is going to be a negative 12 tangent squared of theta. We need two things that add to get the middle term. Now, what could those things be? Well, I think that you'll find that those two things would be 4 times tangent of theta times a negative 3 tangent of theta. If you add those together, you get 1 tangent of theta. That's what the middle term is. If you multiply those two things together, you get negative 12 tangent squared of theta, which is the product of the first term and the third term. Now, the hardest part is finding those numbers or terms in this case. The rest of it's not that bad. So we are taking, and we are going to split the middle term. So the first term doesn't change, 4 tangent squared of theta. The last term doesn't change, minus 3. But this middle term that was plus tangent of theta gets split apart. It's going to get split into a plus 4 tangent of theta and a minus 3 tangent of theta. Notice if you add those, you still get this middle term. We got those from this down here. Once you've split the middle term, this is extremely simple. This is the easiest type of factoring. It's the first type that you learned for algebra. You group the first two terms together, group the last two terms together. Find the GCF of each of those groups. The first group's GCF is 4 times tangent of theta. What are we left with? Tangent of theta plus 1. The second group's GCF is a negative 3. What are we left with? Tangent of theta plus 1. What will happen every time you do this correctly, assuming that it factors, is that these two binomials are going to be the same. So looking at what we have left, this is one term, this is one term. What factors do those terms have in common? They have the binomial, tangent of theta plus 1. Factor that out to the front. What are we left with? 4 tangent of theta minus 3. That is the fully factored version of number 9. Number 10, we could do it the same way we did number 9. We could do it the same way we did number 8. But I'm not going to do that because this is a special type of trinomial called a perfect square trinomial. The reason it's called a perfect square trinomial is that we could take this trinomial and we could break it apart. I'll show you how it breaks apart. We could break it apart into 2 squares and 2 rectangles that when you put them all together, it makes a perfect square. If I take this here and I break it apart evenly, it's going to be cosine squared of theta, cosine squared of theta, which means when you multiply those together, the area of this square is cosine to the 4th of theta. I'm then going to take the square root of this fella, break it apart evenly, 1 and 1. 1 times 1 is 1. That is the area of that square down there. Color code this for your viewing pleasure. If I take this middle term and break it apart evenly, so that, let me explain what I mean by that. That is going to be this rectangle that is cosine of 2 theta. Let me rewrite this. That's a rectangle that's going to be 2 times cosine of 2 theta. If I split this apart, like here, that's going to make each of these rectangles 1 by cosine of 2 theta. This scale that I have here is really bad. That's more accurate. Well, I can take one of these and put them right here. I can take the other and spin it around and put it right here. So the area of this rectangle is cosine squared of theta. This one's cosine squared of theta. There are 2 of those, just like there are 2 of those right here. A lot of explanation. Just trying to give you a visual of how this works. Long story short, long story longer, I should say, to determine if it's a perfect square trinomial, first term has to be a perfect square. Second term, so the first question is the first term a square? It is. Is the last term a square? It is. Question 3, if you double the square root of the first term times the square root of the last term, Is that the same as the middle term? If the answer to all those are yes, then it's a perfect square trinomial. So how does it factor? Take the square root of the first term, put it in the beginning. Square root of the last term, put it in the end. Sign of the middle term goes in between, and this is squared. Now what does this have to do with this big picture that I drew? Well, look at it. This dimension from here to here is cosine squared plus 1. This dimension here is cosine squared plus 1. So the area of the square is cosine squared plus 1 times itself, which is cosine squared plus 1 squared. I think it's awesome. Moving on. On the next series of examples, we will employ this idea of factoring to solve trig equations. Solve the equations below, find solutions on the interval from 0 to 2 pi, get exact values of theta when possible. All right. So the directions for this break down to this. Figure out what theta is. Now, in its current form, this problem is really difficult. What we're going to have to do is we're going to have to get all the terms on the same side and see if factoring is actually going to work. The directions imply that it's going to. So let's say we have 2 sine squared of theta minus sine of theta plus 1 equals 0. When we factor, we know all the terms on the same side, so it's equal to 0. This is a trinomial. It's not a perfect square trinomial. I'm going to split the middle term and factor by grouping. To do that, I need to multiply to get the first term times the last term, which is going to be 2 sine squared of theta times 1, which is just that. Add to get the middle term. What numbers do you think are going to work for that? How about negative 2 sine of theta and 1 sine of theta? That adds to be the middle term, and it multiplies to get, well, scratch that, it doesn't multiply to get that. Oh, I've made a mistake here. This should be a subtract 1. So we are multiplying to get a negative 2 sine squared of theta, so that works. So the first term doesn't change when we're splitting the middle term. The last term doesn't change. The middle term gets split into 2 separate terms. So these 2 terms right here. So we got minus 2 sine of theta plus sine of theta. Notice how that middle term and these two, those 2 terms that get split apart are equivalent to each other. So we haven't changed the equation the way that its value is, we just changed the way that it looks. Once we've done that, group the first 2 together and the last 2 together, find the GCF of each group. This first group's GCF is 2 sine of theta, leaving us with sine of theta minus 1. GCF of the next group is 1, leaving us with sine of theta minus 1. Looking at these 2 terms, they both have the same factor of sine of theta minus 1. So let's factor that out to the front, leaving us with 2 sine of theta plus 1. Once we get to this part, we have to make 2 equations, each of them equal to 0. Because we are multiplying to get 0. So that means that each of these factors have the potential of equaling 0. On the left, if we solve this, we're going to get sine of theta is 1. So what does that make theta? It makes theta sine inverse of 1. When is sine equivalent to 1? It is equivalent to 1 at the top of the unit circle at pi over 2. That's the only time it happens in one period from 0 to 2 pi. Solving the second equation, if we subtract 1 from both sides and then divide by 2, we get sine of theta is negative 1/2, which means theta is sine inverse of negative 1/2. When is sine negative? Sine is negative in quadrants 3 and 4. Makes the reference angle pi over 6. So my answers are 7 pi over 6. And my other answer is going to be 11 pi over 6. It's the angle in standard position. So number 11, the official answers are pi over 2, 7 pi over 6, and 11 pi over 6. Let's not do all these examples. Let's check out number 13. Well, let's not skip. Let's go back and do 12. What is sine of 2 theta equivalent to? Sine of 2 theta is equivalent to 2 sine of theta cosine of theta. That is the double angle identity for sine. If we were to subtract sine of theta from both sides, we get 2 sine of theta cosine of theta minus sine of theta equals 0. If we GCF this, sounds like a bad word, we're going to get sine of theta equals 2 cosine of theta minus 1. Set each factor equal to 0. Sine of theta equals 0. 2 cosine of theta minus 1 equals 0. Solving each of these equations, we're going to get theta is sine inverse of 0. Solving this other equation, we're going to get cosine of theta is a half. Well, when is sine inverse of theta 0? That's on the positive and negative x-axis, theta axis in this case. That's going to be at, the directions say between 0 and 2 pi, not including 0, but including 2 pi. So that's going to be pi and 2 pi. Cosine of theta is 1/2. That means theta is cosine inverse of a half. Cosine is positive when x is positive. That's in quadrants 1 and 4. If that's a half, that makes the angle here pi over 3. So one of my answers here is pi over 3. And then the other answer is going to be 2 pi minus pi over 3, which is going to be 5 pi over 3, I believe. So those are our 4 answers for that. Number 13. Get all the terms on the same side and see if we can factor this mother. We're going to get tangent of 2 theta plus tangent of theta minus 2 equals 0. This is a trinomial. It's not a perfect square trinomial. Lead coefficient's 1, so we don't have to split the middle term. We can just go right to our binomials. I'm going to have tangent of theta. That's the square root of the first term in the first position of my binomials. I need two things that multiply to get -2 and add to get 1. So those things are +2 and a -1. Set each factor equal to 0. So I got tangent of theta +2 equals 0, and tangent of theta -1 equals 0. Tangent of theta is -2. Here I'm going to get tangent of theta is equal to 1. Solving this first one, I'm going to get theta is tangent inverse of -2. Solving the second one, I'm going to get theta is tangent inverse of 1. Now, I don't know how to solve this one. Not without a calculator. Come back to that. I do know how to solve this one. When is tangent 1? Well, it's positive in quadrants 1 and 3. In order to be 1, that means that my reference angle has to be pi over 4. So theta is pi over 4. That's from here to here. And then from here to here, it's going to be 5 pi over 4. This other part, I'm going to have to use the calculator for this. If I put into my calculator tangent inverse of -2, I'm just going to make a note here. This is calculator. I'm going to get theta is -1.107. This is radians. Now that cannot be an answer to the question because that's negative. If I go down here and I draw a reference, some reference triangles, just real quick estimates. As far as pi's go, so this is 0 as far as radians go, I mean. From here to here is pi, which is about 3.14. That means this is about 3.14 divided by 2, which is like 1.5 and change. And this down here is, let me just get a calculator because I'm terrible with numbers. So we got pi, which we know is 3.14. If we divide that by 2, that makes this about 1.57. 3 pi over 2 would make this 4.71. And then 2 pi, we know, is 6.28. So here's why I'm showing you all that. Your calculator gives you this answer, which is not in the normal format that we're used to, which is radians that has pi's in it. It's just a decimal. -1.1 is going to go in this direction, and every 90 degrees is about 1.57. So that means that that puts this angle down here in quadrant 4. Since tangent is negative, it's also negative in quadrant 2. That makes this reference angle 1.07. Well, what does that actually make theta? It's going to make theta pi minus 1.107, and it's going to make theta 2 pi minus 1.107. Using a calculator, that ends up being 2.304 and about 5.176. So those are the 4 things that theta could be for this problem. 14, solve the equation below utilizing sum of difference identities and or double angle identities. Well, I think that you would agree that 4 sine of theta cosine of theta is the same as 2 times 2 sine of theta cosine of theta. It says to solve the equation. It means we want to get theta. Well, I could divide both sides by 2. And then I recognize this is the double angle identity for sine, which is sine of 2 theta. Let's get 2 theta by itself by sine inversing both sides of the equation. But what does that make theta? Well, square root of 2 over 2 is in a 45, 45, 90. And this is supposed to be negative. It was in the previous step, and then I didn't write negative for this one. When is sine negative? Sine's negative in quadrants 3 and 4. My reference angle for this is pi over 4, and this as well. That makes this angle in standard position 2 theta, that is, 5 pi over 4. And it makes this angle 1 pi over 4 short of 8 pi over 4, which is 7 pi over 4. To get theta by itself, I need to cut those in half. Now this is only half my answers because since the original angle was 2 theta, it means I can fit 2 full periods between 0 and 2 pi. So if the directions, which are poor in this case, said what they had been saying, find the answers between 0 and 2 pi, I would add pi to this answer, which is going to be 13 pi over 8. I would add pi to this answer, which is going to be 15 pi over 8. So those are my 4 answers for this. All right, one last problem, 15. 2 cosine of x times cosine of x minus 2 sine of x sine of x. Well, this is a not very cleverly disguised problem. Cosine times cosine is cosine squared. Sine times sine is sine squared. Both of these terms have a 2 in it, so I can factor 2 out to the front. If we were to decide to recognize what this is cosine of 2x. If I divide both sides by 2, I get cosine of 2x is square root of 3 over 2. Now let's figure out, when is cosine positive? Cosine's positive in quadrants 1 and 4. I guess I should get 2x by itself. If I use cosine inverse on both sides, I get cosine inverse is square root of 3 over 2. Square root of 3 over 2 is in a 30, 60, 90. Pi over 6, pi over 3, 90. If x is square root of 3 over 2, that makes this angle up here pi over 6. It makes this pi over 3. Oh, I got that backwards. Let me get rid of one of these and write this so I can see it better. This is square root of 3 over 2. This is a half. That makes this pi over 6, much better. So one of my answers for 2x is pi over 6. The other one is going to be down here in quadrant 4. So it's pi over 6 short of 2 pi, which is going to be 11 pi over 6. If I then get x by itself, same as multiplying both sides by a half, I get pi over 12 and 11 pi over 12. Since the angle is 2x, it means that there are actually 4 answers because my period gets cut in half. I can fit 2 full periods between 0 and 2 pi. So I'm going to add pi to this, and I'm going to add pi to this, which is going to give me 13 pi over 12 and 23 pi over 12. That concludes the notes. I think I ended up doing all the examples for section 10.5.